Hello everyone, welcome back to the channel. This is the last video in transient analysis series. Previously, I had created different videos on analysis of RL circuits as well as RC series circuit. If you haven't checked that videos, the link is provided in the description box. You can check them and then solve the problems which are there in this video. In this video, I will solve three different problems. All of them are on RC series circuit. Let's begin with the first problem. The statement says the circuit shown below has acquired steady state before switching at t equal to 0. Obtain first part Vc0 plus, Vc0 minus, I0 plus and I0 minus. Second part is time constant for t greater than 0, and third part is it for t greater than 0. The circuit is there are two different positions, position 1 and 2. Here we have a 5-volt source. A capacitor over here. Which is moved from position 1 to 2 at t equal to 0. Capacitor has value 2 microfarad. Sorry, this is not 16, this is 10 kilo ohm. So in order to find out the voltage, Vc0 plus means voltage just after the switching, voltage Vc minus voltage just before the switching. In order to obtain these two, we need to calculate voltage across the capacitor before switching, that is when the switch is connected in position 1. So let's draw the circuit again for before switching conditions in order to calculate Vc0 plus and Vc. So Vc is this and I is the current over here which we need to calculate. So before switching, switch was in position 1, a 10 kilo ohm resistance, 5-volt source. They are connected in series with the capacitor. Since the circuit is connected in this position for long time, so the capacitor will behave as an open circuit. So as this is an open circuit, so current through this 10 kilo ohm resistance is 0. So whole 5-volt supplied by this voltage source appears as voltage across the capacitor, that is Vc0. So Vc 0 minus, which is same as Vc0, same as Vc0 plus, is actually 5 volts, because capacitor has a property that it opposes the instantaneous change in voltage. So whatever the voltage is there just before the switching, that will be same as after the switching as well as at the instant of switching. 0 minus just before the switching, 0 instant of switching, 0 plus just after the switching. So all of them are actually 5 volt. So this is what was asked in the first part. Then we need to calculate the current. For that we need to calculate the voltage of the capacitor. So let's move on to after switching condition. After switching, the switch is moved to position 2. Source and 10 kilo ohm resistance, they are no more in connection with the capacitor. This is the circuit now. Now in this position, when the switch is closed, the capacitor which was initially charged to 5 volts, that will start discharging, and after a long time, when the steady state conditions have been reached, it will discharge completely. Since we don't have any other active source over here, so the voltage across the capacitor will finally fall to 0. So Vc infinity is 0. We also need to find out the time constant for t greater than 0. Time constant tau is R equivalent into C. Now from after switching conditions, 5 kilo ohm, these are the capacitor terminals, 10 kilo ohm, voltage source need to be replaced by short circuit. Here we need to calculate R equivalent. So R equivalent is just a single resistance, because in between the capacitor terminals we have only one resistance of 5 kilo ohm. So R equivalent is 5 kilo ohm. Now when we use the value of capacitor and R equivalent, 5 into 10 raised to power 3, capacitor was 2 microfarad, to 2 into 10 raised to power minus 6. So it's 0.01 second. Tau is 0.01 second. Now we can calculate the voltage across capacitor VCT as Vc infinity plus Vc0 minus Vc infinity into e raised to power minus t by tau. Vc infinity is 0, Vc0 is 5 minus 0 into e raised to power minus t by 0.01. So Vct is 5 into e raised to power minus 100 t volts. So this is the value of voltage across the capacitor for t greater than 0. But the question was that we had to find out the current I for t greater than 0, which is the current through this 5 kilo ohm resistance. Now how to find out this? We can actually find out that what is the current through the capacitor, and then we can calculate the current. Now when we come to this after switching condition, once a capacitor is charged, from this we can see that this terminal of capacitor is going to positive and this one is going to be negative, and accordingly the capacitor will discharge in this way. So current through the capacitor will flow in this direction. So when the current through this will flow in this direction, this is as per that how the current flow was there, like this. So current will continue to flow like this. This I is given in downward direction. So if we find out the value of current through capacitor, then we can find out I by simply I is equal to minus of ICT. So if we find out this ICT, we can have the value of I as well. Now how can we find out the current through capacitor? It can be found by using C dVc by dt. Now the capacitor value was 2 microfarad, 2 into 10 raised to a minus 6, and we have to use the value of Vc as 5 into e raised to a minus 100, 5 into e raised to a minus 100t by dt. So differentiation of this will give us the value of this current as 5 into minus 100 into e raised to a minus 100t. So when we find it out, then it comes minus 100 into 10 raised to a minus, sorry, minus 10 raised to a minus 3 into e raised to a minus 100t. So we can say it's e raised to power minus e raised to a power minus 100t milliamperes. Now this is the value of current through capacitor. Since I has opposite direction as current through capacitor, so it is e raised to a minus 100t milliamperes. Also we need to find out the value of current at t equal to 0 plus and t equal to 0 minus. So t equal to 0 minus, before switching, since this 5 kilo ohm resistance was not there in the circuit, so current through the this I 0 minus, it's 0, and this is not the value of ICT, this is the value of I. Please note this correction, this is not ICT, this is I. And I0 plus, that we can calculate by putting this t as 0, so I0 plus is 1 milliampere. So this is how we obtain different answers by just calculating the voltage across the capacitor. Now let's move on to the second problem. Second problem says, in the network shown in figure, the steady state is reached with with the switch open at t equal to 0, switch is closed, find VCT for t greater than 0. We have a switch over here, five microfarad capacitor, 5 kilo ohm, 1 kilo ohm, 3 kilo ohm, 2 kilo ohm, and this switch is closed at t equal to 0. VCT will be calculated as VC infinity plus VC0 minus VC infinity into e raised to a minus t by tau. So calculate the value of voltage across the capacitor. This is Vc, which we need to calculate. Voltage across the capacitor before switching, that is Vc0, Vc infinity after switching, tau again after switching. First step is calculations from before switching conditions. Before switching, we have all the resistances. The switch is open. Now, in this path, we don't have any active source. Since we don't have any active source, so irrespective of what is the value of these resistances, the voltage across this 5 microfarad capacitor is actually 0. So Vc0 is actually 0. Then we have after switching, the switch is closed. After reaching the steady state conditions, this capacitor will start behaving as an open circuit. Now we need to calculate that what is the voltage across this capacitor. Now for calculating the voltage across capacitor, we need to calculate the potential difference between these two terminals. Since this side of circuit is open, so current through 5 kilo ohm resistance is 0. There is no drop across 5 kilo ohm resistance. If we find out that what is the potential difference between these two terminals, then we can have the value of voltage across the capacitor at t equal to infinity. For finding out that, we will find out that what's the current in this loop. So as per the assumed direction of current, the voltage drop polarity is like this. So since all the resistances are in kilo ohm, so I will write 2 into I plus 3 into I plus 1 into I to 10 raised to power 3. All of them are multiplied by 10 raised to power 3 because of kilo ohm. Then plus 6 equal to 0. So this will give us the value of I as minus 6 milliamperes. Sorry, not minus 6, minus 1 milliampere. It's minus 1 milliampere. To find out the voltage across the capacitor, if this terminal is considered positive, this one is negative, we can apply KVL in this open loop. So when we apply KVL in this open loop, starting from this Vc infinity minus 6. Now since negative sign is coming first, so I am writing minus 1 into 10 raised to power 3 into current value into, we can write I equal to 0. Vc infinity will be equal to 6 plus I into 10 raised to power 3. Now let's use the value of I, which is minus 1 milliamperes minus 10 raised to power 3 into 10 raised to power 3. So Vc infinity is actually 5 volt. So after switching, we get the voltage across the capacitor as 5 volt once the steady state conditions have been reached. So next step is we need to calculate the time constant. Now for time constant, we need to draw the circuit. After switching, the voltage source has to be replaced by short circuit. 3 kilo ohm resistance, 2 kilo ohm, switch is short circuit, then 1 kilo ohm, voltage source is to be replaced by short circuit, 5 kilo ohm, and these are the capacitor terminals from where we have to find out R equivalent. R equivalent is 5 in parallel with 1, and that is in series with 5. 5 plus 5 in parallel with 1, so which will give us the value of equivalent resistance as 5.833 kilo ohm. Tau R equivalent into C, 5.833 into 10 raised to power 3. The value of capacitance is 5 microfarad into 5 into 10 raised to power minus 6. So it is 41.667 into 10 raised to power minus 3 seconds. So voltage VCT, which is equal to V infinity. V infinity is 5 plus V0 0 minus V infinity 5 into e raised to power minus t by tau 41.667 into 10 raised to power minus 3. So which will give us answer of VCT as 5 into 1 minus e raised to power minus 24 t volts. This is the answer. So the last problem which I am considering over here, if in figure the switch K is closed at t equal to 0, find the time when the current from battery reaches to 500 milliampere. Here we have a switch which is closed at t equal to 0. Fifty ohm resistance, 70 ohm, 100 microfarad. This is a circuit. Now it's given in the problem that current from battery reaches 500 milliamperes, means this current is 500 milliamperes after switching when the switch is closed. So when the switch is closed, this 10 volt will be connected in parallel with 50 ohm. So if the current through this 50 ohm resistance is I1 and current through the series combination of resistance and capacitance is I2, then 500 milliampere is actually equal to I1 plus I2. And I1 is equal to voltage upon resistance, that is 200 milliampere. So from here we get the value of I2 as 300 milliampere. That is the current through capacitance, that is 300 milliampere. We need to drive the expression of current through the capacitor and equate that to 300 milliampere in order to know the time to reach this current, and this current from battery at 500. So this one is 300 milliampere. We know its value, we need to find its expression. In order to find its expression, I2 will be equal to C dVc by dt, where Vc will be the voltage across the capacitor. And Vc can be found by Vc infinity plus Vc0 minus Vc infinity into e raised by t by tau. This is the expression. So let's find out the value of voltage across the capacitor before switching, after switching, time constant, and then calculate the time. For before switching, the switch is open. Two resistances and capacitor, they are connected like this: 70 ohm, 50 ohm, and this capacitor. Since we don't have any source connected to it, so the voltage across the capacitor is 0. Vc0 is actually 0. Then after switching, the switch is closed. 10-volt source, 50 ohm resistance, 70 ohm resistance. Here we have capacitor. Once the steady state conditions are achieved by the circuit, then this capacitor will behave as an open circuit. So when it is replaced by open circuit, the current through 70 ohm resistance will be 0. There is no drop across 70 ohm resistance. So whatever the voltage is there across this 50 ohm, same is the voltage across the capacitor. Now this 50 ohm resistance, that is connected in series with this 10 volt. So whole of this 10 volt will appear across this 50 ohm. So Vc infinity is directly 10, 10 volts. We don't need to do any calculations. We just need to understand the concept that how we are getting this one as 10 volts. There is no drop across 70 ohm resistance. This 10 volt and 50 ohm, they are in series. So whole 10 volt is appearing across the 50 ohm resistance, that is the voltage across the capacitor. So the last step is we need to calculate time constant tau, which is R equivalent into C. For time constant, the voltage source has to be replaced by short circuit, 50 ohm, 70 ohm, R equivalent. Now this 50 ohm is in parallel with the short circuit. So it will actually get shorted. It's no more there in the circuit. So R equivalent is only 70 ohm and tau is 70 into capacitor has value of 100 microfarads. 100 into 10 raised to the minus 6. So it's 7 into 10 raised to the minus 3 seconds. Tau is 7 into 10 raised to the minus 3 seconds. So voltage across the capacitor is V infinity plus V0 minus V infinity into e raised to the minus t by tau, that is 7 into 10 raised to the minus 3. So this one is 10 into 1 minus e raised to the minus 1000 by 7 t. This is the value of voltage across the through the capacitor. Then I is equal to C dVc by dt. C is 100 into 10 raised to power minus 6 d by dt of 10 minus e raised to power minus 1000 by 7 t. 10 raised to power minus 4. Differentiation of this one is 10 into 1 minus this. 10 into 0 minus e raised to power minus 1000 t by 7 into minus 1000 by 7. So minus minus plus, and when we multiply all of them, then it becomes 1 by 7 into e raised to power minus 1000 by 70. This is the value of I, and this should be equal to 300 milliamperes. So 1 by 7 into e raised to power minus 1000 t by 7 is equal to 300 into 10 raised to power minus 3. So we can find out it by taking the natural log on this side, which will give us the value of t by 0.007 as 0.7419, and time required to current to reach to 300 milliampere through the capacitor and 500 milliamperes from the source is 5.2 milliseconds. So this we can calculate by taking the natural log on this side. When we take natural log on this side, it will be minus 1000 t by 7, and this side the natural log value, and we get the value of time as 5.2 millisecond. I hope these problems are sufficient to clear the transient analysis. If you want more problems to be solved on the transient analysis, please let me know that in the comment section. And if you find the content useful, please consider subscribing the channel. Thank you for watching the video.